Hi there, this is MG5004 DE5418, topic 8, and we're going to look at vectors. Much of the work of engineers and scientists involve forces. I'm sure you know that. And ensuring the structural integrity of a building or a bridge involves knowing the forces that are acting on the system and designing the structural members to withstand those forces. Now, forces are three-dimensional quantities, and they provide one of the most common examples of vectors. So associated with these vectors are things like velocity and acceleration. And what we need to do is we need to construct an algebraic theory for the manipulation of vectors and apply this to simple problems. Vectors are developed quite a while ago in the 19th century, and they're a convenient, compact way of dealing with multidimensional situations. They need to be precise. For example, anybody that's involved in robotics, then this is this. And often algorithms are written for robots in terms of matrices and vectors. You'll need to differentiate between a scalar, and a scalar can be fully described by a single number. For example, the mass of something is 0.4 kilos or 4 kilos, and a vector requires direction as well as magnitude. For example, the force applied to make the box in the diagram move, and you get different results by applying the force in different directions. In the diagram here, there's two things going on. There's the distance is 10 meters, but there's also, remember, displacement, and the displacement is 10 meters from A to B, so it's got direction involved. Speed is a scalar, 20 kilometers an hour. Distance is a scalar, it's just a single number, 20 kilometers. Velocity is a vector, for example, 20 kilometers an hour due south. Mass is a scalar quantity. Weight is a vector since it's got mass and some force, and it's got a downward force. In this diagram, we've got a vector since it's got magnitude and direction. We can write vectors in different ways. We can write them as this idea with an arrowhead. We can write them as a bold little a, or we can write them as with a little squiggle underneath, or sometimes you'll see them with a little squiggle on the top. All of them are representing vectors. The modulus, or the magnitude of this force, is 5 newtons, and in the next slide we represent it as a vector. So now the magnitude of F is 5 newtons, and it's got a direction. We can write the magnitude as that, or with a little squiggle on the top, or like that. All of those mean the modulus, or the magnitude of that vector. Looking at the top diagram, vectors are equal if their magnitude is the same and their direction is the same. So AB is equal to CD. They don't have to start in the same place. So we're talking here about free vectors. And they're equal. They have equal length, equal magnitude. And they have equal direction, or the same direction. If we look at the second diagram, then the opposite vector A has the opposite direction to A. So it's the same length, but it's going in the opposite direction. Here we have an object that's subjected to 2 forces. One of them's 3 newtons vertically down, and one of them's 8 newtons horizontally to the right. So let's see what happens as a result of that. Well, in order to do that, we need to look at how we can add vectors. We add vectors by placing them head to tail and looking at the combined effect. Sometimes this is called the triangle law, and of course there's going to be rules that affect these. So suppose we say that A plus B is equal to C, then A plus B is going to be the same as B plus A. So vector addition is commutative, and A plus B plus C is going to be exactly the same as A plus B plus C. That's the associative rule. So the associative rule works for vector addition, and also if we have a scalar, something like lambda, then it's distributive as well. Like that. It's often typical as well to write a triangle and use slightly different notation. We've got A, B, and C, and so AC is like that, BC is like that, and AB is like that. Then we could say that AB, the vector AB, plus the vector BC is equal to the vector AC. So the resultant of two vectors is their sum. It's obtained by adding them. That's just a repeat slide of the previous one. So AB plus BC is equal to AC. Let's go back now to the block that's subjected to two forces, one 3 newtons out to the right and another one 2 newtons vertically down. So the resultant is R, because if we add the force 1 onto the end of force 2, we would get R. So we could say that R is equal to force 1 plus force 2. And the modulus of R is going to be the square root of 3 squared plus 2 squared, which is root 13n. And it's acting in a particular direction. What we can do is we can look at a force and we can decompose it into its two perpendicular forces. So F sine 1 and F cos theta. Back with ordinary trigonometry now, to resolve this force into its two components, the horizontal component is going to be 15 times cos of 40. Work that out on a calculator, about 11.5. And that's going horizontally. And the vertical component is going to be 15 times sine of 40. And that'll be about 9 point something. So we've broken it up into the two forces, a horizontal one and a vertical one, working backwards from knowing the angle and the magnitude. As you would imagine, it's easy to define subtraction as being A plus the negative of B. So if we have in a triangle from O to B to A, if I wanted to find BA is equal to OA minus OB. Like that. All we've got here is that q minus p is the same as q plus negative p, which again you would expect. We've already introduced the idea of multiplying by a scalar some number, and we know that if that number is lambda, we know that this is true. And also, if we have some number plus another number, and also if we're multiplying like that. Now, what we've got here is we need to think of the idea of a unit vector, and a unit vector has a length of 1, a modulus of 1. So if you look at the second diagram, suppose we've got A, and suppose A has a modulus of 3, then the unit vector is going to have a length of 1. So in this case, the unit vector is a third of A, like that. You know about putting a point onto a two-dimensional coordinate frame, like a coordinate geometry that we've already done. But what we're actually going to do now is we're going to talk about this kind of thing in terms of unit vectors. So we're going to have a triangle like that with a hypotenuse of r and x that way, and that's your y dimension there. And what we're going to do is we're going to call this AI, and we're going to call this BJ. Now I and J and K, if we're in 3D, are the unit vectors in the direction of the X, Y, and Z axes. And they're not to be confused with complex numbers. In the top left diagram, all of these vectors are multiples of I, the unit vector in the X direction. In the bottom diagram, I'm just going to make it a little smaller. In the bottom right, all of these vectors are multiples of J, the unit vector in the Y direction. So these are multiples of I. Let's revisit vector addition. In this case here, in this diagram, we've got that R is equal to AI plus BJ. And we can write that as R is equal to AB. And A and B are called the I and J components of R, respectively. So now we can see how we can add vectors in this format. If we've got R1 is equal to AX and AY, and R2 is equal to bx and by, then a plus b, which is r, is going to be ax plus bx in the I direction plus ay plus by in the j direction. And we can also multiply a vector written like this by a scalar. So if we've got that a is equal to axi plus ayj, then ki, some scalar, is going to be kaxi plus kayj. If our vector now starts at the origin, we call it a position vector. So if it starts at the origin, then we call it a position vector, and we can write it as r equals xi plus yj. It's fixed, it's not free, it starts at the origin. So we could also write it as xy, like that. It's got to be relative to something, so it's got to be fixed. We can find the lengths of these, or the magnitudes of these vectors. So if we've got that r is equal to xi plus yj, then the magnitude of r is equal to the square root of x squared plus y squared, which is what you'd expect. So let's have a look at r1. r1 is 3 plus 4j, so that's r1. So the magnitude of that would be the square root of 9 plus 16, which is 5. Let's have a look at r2. r2 is going to be negative 2i plus 5j, and the magnitude of that is going to be the square root of 4 plus 25, which is root 29. We'll just leave it like that because that's the most accurate form of it. Looking at r3, r3 is negative 3i minus 2j. So the magnitude of that is going to be the square root of 9 plus 4, which is root 13. So what we've done is we've found the lengths of each of those position vectors. Now we talk about things like the direction ratio, and in this case the direction ratio of OP is defined by, or defined as, 4, 5. So to move in the direction of the line, for every 4 units in the x direction, you've got to go 5 in the y direction. We talk about the direction cosines, and the direction cosines of this vector are the cosines of the angles between the vector and each of the positive axes. That's just how they're defined. So we talk about L as being cos alpha, and we talk about M as being cos beta. And if we had 3 dimensions, we'd talk about N as being cos gamma. So in this particular example, L is equal to cos alpha, which is equal to 4 over root 41, because the magnitude is root 41. M is cos beta, so that's 5 over root 41. So generalizing then, that if R is equal to a standard vector like that, then the direction ratio is A to B, and the direction cosines, these are the cosines of the angles between each of the axes. So L is A over the square root of A squared plus B squared, and M is B over the square root of A squared plus B squared. Now, if we think about it, L squared plus M squared must equal 1, and you can prove it just by doing some algebra there, adding the fraction. In 3 dimensions, then we're going to have a vector R, which is going to be xi plus yj plus zk, and we could write that as x, y, z. On the next slide, I'll show you where L and M and N are, and the 3 causes are. So we've got the lengths of that vector. The length of the vector was just an extension of Pythagoras, and then L is going to be the cosine of alpha, which is between the vector and the x-axis, so that'll be x over that, and M would be cos of beta, which is the angle between the vector and the y-axis, and N this time, because it's in 3 dimensions, is going to be the cosine of gamma, which is the angle between that and the z direction, and again you can prove that L squared plus M squared plus N squared is equal to 1. And it's the same kind of thing as we saw in 2 dimensions. You can prove it algebraically. So the final thing I want to say here, the position vector of P, so the position vector of P is R, which is OP.